Welcome back. We're lecture 6 today. We left a problem kind of pending yesterday. I think we set up all the arithmetic for it in a Simpson's rule. It's problem 10. 421, does that page sound right? What kind of decimal approximations were we able to come up with? I've got one, but I'm not going to tell you till I get one from you and see if I'm in the ballpark, because I was...
0.898.
Okay.
That's what I got.
Yeah.
Okay. 0.898, 014. Okay. That's what I got too. Any problem with that decimal for the approximate area under that curve? What was it? 1 over 1 plus t squared plus t to the fourth, right? From 0 to 3? Okay. Just to see that Simpson's rule kind of gives a better number, I looked up the trapezoidal approximation is 0.895, probably pretty good, different in the third decimal place, and the midpoint approximation was 0.895 also. So seems to be that this is giving us a different answer, probably a better answer. I also took a few moments to try to generate the error bound for this, but I didn't make it to the fourth derivative. I started and got into the second derivative. It's kind of an ugly series of derivatives, so let's just suffice it to say that it's a pretty good approximation. Okay, I didn't maximize the value of the fourth derivative. This would be interesting, I think. Interesting to me, maybe not to you. Take this problem that we were given. And let our old friend do it. Okay? Put that problem into Maple and see what it gives you. I'd kind of like to see how accurate our 0.898. I feel pretty comfortable with those 3 decimal places. Maybe not quite so comfortable with the next set of decimal places, but take a few moments and do that. And I kind of wonder, too, what Maple is actually using. If you did this problem without the limits of integration and you did an indefinite integral, that might give us a clue as to how Maple is actually doing this problem. And then we throw in the limits of integration, and it. I think I'll run that through, report on that in tomorrow's class. Okay. Yes.
To evaluate the integral, it gives you 0.89537.
Okay.
Though it doesn't do it very accurately on calculators, I don't think, because it uses just the. It doesn't use as many rectangles as I've done it before on Maple and on a calculator, and in Maple it always comes out with a different answer.
Okay.
Yeah.
So that would lead me to believe I'd have to look at the manual that goes along with the calculator. But sometimes it'll tell you how it's doing a problem. Like a lot of manuals and calculators will tell you that it's obviously your calculator doesn't know what a sine is. You know, it's not a very smart machine. It's been kind of programmed to do problems certain ways, so it's doing sines, and we'll do this as part of this course, Taylor series and Taylor polynomials. It's doing a sine in that fashion. So I don't know if it goes to like the 7th power, the 9th power, or the 13th power, or whatever, but that leads me to believe that that calculator is probably doing either midpoint or trapezoidal approximation. Which is kind of interesting that you find this stuff out after you study this stuff, and then you say, oh, well, that's what my calculator's been doing. So I don't know. I just mentioned something that we'll touch on later, and some of the things we'll do today, we'll come back to revisit them later in this course when we get to Chapter 8. It's slightly different, but similar. Sine of x, for example, I just mentioned a Taylor series or a Taylor polynomial. You don't need to know this now, but since it was brought up, Sine of x, is that an even function or an odd function?
Odd.
That's an odd function, right? Even functions have symmetry with respect to the y-axis. What type of symmetry does sine have?
X-axis. Yeah.
Not the x-axis.
Origin.
Origin. Symmetry with respect to the origin. If it had symmetry with respect to the x-axis, it wouldn't be a function, right? So symmetry with respect to the origin, it's an odd function. So we will discover with Taylor and Maclaurin series and generating Taylor and Maclaurin polynomials. Have any of you had those before? In a math class you've had some Taylor series? Anybody else? It does involve higher order derivatives. That's how you get to these. But there's the pattern that your calculator is probably using to do the sine of, let's say, pi over 4. So whatever goes here, pi over 4 goes there, pi over 4 goes there, and there, and there. So I don't know how deep into this process your calculator is working, whether it goes to the 9th power over 9 factorial or the 11th power over 11 factorial, but this is a way of evaluating the sine of an angle that clearly that's not trigonometric. In fact, that's pretty polynomial looking, isn't it? X cubed, x to the 5th, x to the 7th. Kind of looks like a polynomial. And in fact, that's where it gets its name, the Taylor polynomial or the Maclaurin polynomial. So that's what I meant when I said that's how your calculator is doing the sine. We'll revisit that in Chapter 8, actually near the end of this course. All right, new material today. I guess. Any further issues with trapezoidal approximation or Simpson's rule approximation for area under a curve? Okay. So the next section deals with improper integrals. There are two types of these. We'll, I know, get to the first type today, hopefully get a fairly thorough treatment. And then I don't know how the time's going to work out, but we may get to the type 2 today. If not, we'll have plenty of time for that tomorrow. So what is an improper integral? An improper integral of the first type, we're used to having a number as the lower limit of integration and another number as the upper limit of integration. You wouldn't think a problem was going to be an issue if you encountered this. We're integrating 1 over x dx from 2 to 7. It's starting at 2. It's stopping at 7. We're going to have a numerical answer. It's the area under this curve. In fact, we know what that is. It's the natural log, right, of 7 minus the natural log of 2, or the natural log of 7/2 would be a way to put those together. But what we're going to do with improper integrals is we're going to go from 2, and in fact we're not going to stop it at all on the other end. We're going to let it run all the way to infinity. Kind of seems improper, right? Doesn't seem like we're going to be able to find the answer to that. Sometimes these problems have an answer and sometimes they don't. And we'll try to look at some examples today where they have an answer, what that curve looks like, ones that don't have an answer, what that curve looks like. So we'll get some visuals, not that visuals are going to tell us the answer. But there's our curve, 1 over x, and we want to go from 2 all the way out to infinity. We're not going to close it off on the other end. I know what I think. I know what I thought when I saw these the first time. I thought, well, there's no way it's going to have an answer because we're not stopping it at a certain number. None of these problems is ever going to have an answer. This one, in fact, is not going to have an answer. But let's evaluate why it's not going to have an answer. Let's slightly change it. And the curve looks very, very similar to this one. And in fact, it will have an answer. So how do we approach this problem so that we can evaluate things kind of in the right order and let things approach infinity when they need to be approaching infinity? The first step is to, for lack of better terminology, is to delay the bad value to the end of the problem. The bad value is infinity, so let's go from 2 to something, a, and then the very last step of the problem will let a approach infinitely large numbers. So we integrate, saving this approaching of infinity till the end of the problem. We integrate 1 over x dx. That's the natural log of the absolute value of x. We evaluate it from 2 to a. So that is the natural log of the absolute value of a. I don't think we have to worry too much about absolute value here because we're starting at 2 and moving to the right, so it's almost irrelevant. When we put in 2, we get natural log of 2. So part of it we're going to know and part of it we're not going to know. So now we're done integrating, we're done evaluating. Let's see what happens as a approaches infinitely large numbers. So we want a to be 10, not very large, a to be 1,000, a to be 100,000, and so on. What happens to the natural log of a as a gets larger and larger and larger? It gets larger, right? Isn't the natural log of 10 a pretty small number? When you put 1,000 in it, don't we get a bigger number when we take the natural log of 1,000? How about the natural log of 100,000? Is it even bigger than this? So as you keep putting in larger and larger numbers for a, the natural log of a continues to get larger and larger. So this thing approaches infinity, not necessarily at the same rate that a is approaching infinity, but this thing gets larger and larger and larger. It's not bounded at all. So if this is not bounded, are we going to save it by subtracting the natural log of 2 from it? No. So the limit does not exist. So we will say that this is a convergent, or let's just, I'm sorry, not convergent, divergent. This integral diverges. We don't converge on a finite number for our answer. If we don't get a finite number for our answer, then it does not converge, therefore it diverges. So it doesn't have an answer. So can we find the area under this curve? F of x equals 1 over x from 2 to infinity? We cannot. So that kind of seems, the answer seems like what we thought it would be prior to doing the problem. You better cap it off on the other end or you're not going to be able to find the answer. Questions on this one? Okay, I'm going to slightly change the function. It does change the visual appearance, but not drastically. But we're going to change the function now to, instead of 1 over x, 1 over x squared. This is why the visual appearance of the function is not going to really, I mean, you need to know that it's decreasing. It doesn't have a chance of converging if it's not descending on the x-axis or asymptotic to the x-axis. So what is the critical issue is how fast is it closing in on the x-axis. So let me actually, let's say this is 1 over x, and let's plot a few points here. Let's say this is 1. What's the corresponding y value of, what's y when x is 1? It's 1. Okay? Is that going to be any different on this one? No. It's going to be 1 over 1 squared. So we've got this point in common between the two. And we're not really starting till 2, so let's see where we are at 2. In this curve, 1 over x, when x is 2, where are we?
1/2.
1/2? Is that right? 1 over 2? And in the other curve, the new one, 1 over x squared, where are we? 1/4? So it appears that we're kind of underneath this one. Let's continue out here at, let's say, 5. Where are we on the 1 over x curve? 1/5, right? Where are we on the 1 over x squared curve? 1/25. Isn't it a very similar looking curve? Kind of descends like this one does. So we're starting closer to the axis, and we get there a whole lot quicker. Now, does that guarantee the fact that it's going to converge? It does not. But in fact, we're going to find that this one does converge, and we can get an answer to this from 2 all the way to infinity. That's interesting. So what do? We delay the bad value to the end of the problem, 2 to something, and we'll let that something approach infinity. This is not a natural log, never has been a natural log, is not currently a natural log, and just for future reference, never will be a natural log. When do we have a natural log integrand? Okay, a number, constant, 1 over what? X to the first, right? It's got to be x to the first down there to be a natural log. Well, we don't have an x to the first, so that kind of follows the normal exponent rule where you add 1 to the power, right? Divide by the new power. So if it helps to write this as x to the negative second so that we're not tempted to call this a natural log integrand. So what's the integral of x to the negative second dx?
No.
That's right.
X to the third. No, -3.
Add 1, right?
X to the -1.
X to the -1 over -1, right? That's our rule. Add 1 to the power, divide by the new power. If we were integrating x to the 5th, we'd get x to the 6th over 6. So we're integrating x to the negative second, x to the -1 over -1. We're evaluating that from 2 to b. Let's rewrite x to the -1 over -1. What's an easier way of kind of putting things where they belong?
-1 over x.
-1 over x. So we just rewrote it. That's where stuff belongs anyway. Will you find the fact that we've got the limit as b approaches infinity, will you find that somewhat annoying to have to write down several times? Yes, you will. I also find that somewhat annoying to have to write that down, but I am going to save that value to the end of the problem. So I'll put in the upper limit, -1 over b. Put in the lower limit, -1 over 2. And then anything that I need to kind of simplify, I'll do that in my next step, and I should be done except for the so-called bad value. Minus -1/2, that's a half. And then we've got -1 over b. You don't have to write the positive term first and the negative term second. Keep them in the order they were in the original problem, it's fine. Now we're done simplifying except for allowing b to approach infinity. What happens to this term, 1 over b, as we allow b to approach infinity?
Goes to 0.
It disappears, doesn't it? Approaches 0. So this term, in the previous problem, as we kept putting in larger and larger numbers, the natural log of that larger and larger number itself got larger. Here, because of its location, denominator, 1 over tremendously large numbers, that in essence disappears. So we end up with an answer. We get an answer to this. So what's the area under this curve from 2 all the way to infinity?
1/2.
It's 1/2. So it does converge. Now that seems counterintuitive, that you could start this thing at 2, so kind of the red region right here, start it at 2 and let it run all the way to infinity. And if you let it run all the way to infinity, you would get an answer of 1/2. But it's true. Suppose we did this instead. Suppose we took the same curve, and let's start at 2, same value, and let's end at 600,000. Let's draw a diagram. Let's not. Okay? Tell me what the answer is.
Same thing.
Very, very close to 1/2, but less than 1/2, right? So I'll just call it 1/2 with a little superscripted minus there. It's very close to 1/2, but it's less than 1/2, because what do we have to do to get 1/2?
Subtract
You
1.
have to let it go all the way to infinity. That's not infinity. It's way on out there. But so we're going to get some number that's very, very close to 1/2. The only way we could get exactly 1/2 is to not stop this thing at 600,000, but let it go on to infinity. So it is possible they can diverge. In fact, that seems pretty intuitive. It is possible, which seems counterintuitive, that they can converge. This is kind of skipping a little bit. Actually, let me put this up here first. So these are our type 1 integrals. Hopefully we can kind of get through this today and look at the type 2. The fact that it's type 1, don't remember that. They're just 2 categories that we're going to deal with. So if the function exists for every number t greater than or equal to a, what we want to do if we're going from a to infinity is farm that bad value out to the end of the problem and then make that the last step of our problem, provided this limit exists. Or the other way, we could have the bad value on the other end. In fact, we're going to look at a problem that has a bad value on both ends next. If we're going from negative infinity to b, then it's okay to start at t and go to b as long as we, last step of the problem, allow t to approach negative infinity. So we're going to have potentially a bad value up here or a bad value here, or in some cases we're going to have a bad value on both ends. Now what we're going to do on the next example, because we're going to have a bad value on both ends, is break it up into pieces and go from negative infinity to some convenient value. And that's good as long as we pick up at that same convenient value and go the other way out to positive infinity. So these are kind of the 3 categories that fall into this type. So we actually see the bad value, or in this case the bad values in the problem, and then we try to delay that till the end of the problem. So let's see one with a bad value on either end. Probably should not do this example next, but I think we'll be okay to do this, and then we'll try to summarize some of the things we've been finding along the way. Does that integrand look at all familiar?
Yeah.
Inverse tangent, right?
Yeah.
So we know that the derivative of inverse tangent is 1 over 1 plus x squared. Therefore, the integral of that 1 over 1 plus x squared is going to be inverse tangent. So we know that both directions. It's certainly going to come into play on this problem. This may or may not be helpful on all problems, but it is going to be helpful on this problem. Does this problem have any, if we were to picture this, does it have any symmetry?
Yes. No. Origin. Or, no.
One of the tests for symmetry is the f of x equal to the f of negative x. Who remembers what symmetry we're testing for right there?
Origin. No.
You get the same y value when you put in x as you do when you put in negative x. That's symmetry to the y-axis, right? Is that true on this particular function? Is the f of x, do you get the same thing when you put in x that you do when you put in the negative of x?
Yes.
It is true. So this thing does have symmetry to the y-axis. If you were to either physically plot enough points or put this in on your graphing calculator, when x is 0, what do we get? We get 1. And if you plot some more points, I think you'll see this graph do something like this. Therefore, its symmetric image over here does the same thing, right? So because we have symmetry, we can take this problem, which has 2 bad values, and rewrite it in terms of a problem that has 1 bad value, which is kind of what they said on that summary we're allowed to do. So if we find this area, if it's possible to find it, what do we have to do to get the whole area?
Find the others.
Find it twice.
Add it together.
Multiply it by 2, right? Double it. We've got the same bounded number of square units here as we're going to have over here. So let's change this problem to, let's go from 0 to infinity and double it. So technically what's behind this is we can go from negative infinity to 0, and then again from 0 to positive infinity. We've split it up into 2 pieces, but the 2 pieces happen to be exactly alike. So we don't need the 2 pieces. Let's just talk about one of them and double the answer. So I'm going to rewrite that up here. And let's do what we're supposed to do. I'm just going to bring the 2 all the way out in front. Let's go from 0 to something. What is the integral of 1 over 1 plus x squared? Inverse tangent. So I know sometimes in math class, we work with something, we know the derivative rule, we throw it in reverse, we get this antiderivative rule. We are going to be forced in this problem to think about what inverse tangent is and how is that function, inverse tangent, different from but yet somewhat like the tangent function. So we want inverse tangent r minus inverse tangent 0. We don't know what r is technically yet. We know what's eventually going to happen to r. How about inverse tangent of 0? What's the question you ask yourself when you have inverse tangent of 0?
Tangent of what?
There we go. What has 0 for its tangent, right? What is the angle in radian measure that has 0 for its tangent, or as he stated, Jacob, right?
Yes.
Tangent of something equals 0. What is that?
0.
What angle can we take the tangent of and get 0? 0? Right? Isn't the tangent of 0 0? So this itself is 0. Why? Because the tangent of 0 degrees or 0 radians is 0. So this disappears. Now here comes a similar question, but it's a little more bizarre, because now what's going to happen to r? R is going to approach infinity. What angle can we take the tangent of and get, in this case, positive infinity? And it does have an answer.
90.
Okay, 90 degrees, which would be
Pi over 2.
pi over 2. Isn't the tangent of pi over 2 radians positive infinity, right? So as we approach, this is where this comes into play. It's never actually infinity. It's approaching positive infinity. So as r gets larger and larger and larger, what angle can we take the tangent of that allows us to get this number that is more and more and more positive? It's pi over 2, right? Just a tangent graph. The tangent of 0 is 0. We kind of visited that up here. But we know it's asymptotic here. But what happens to the tangent as we get closer and closer to pi over 2? Don't the values get larger and larger and larger? So we're reversing that. As these values get larger and larger and larger, what angle are we getting closer and closer to?
Pi over 2.
Pi over 2, right? That's kind of bizarre that you've got infinity in this problem, inverse tangent of infinity. Maybe that's not the correct way. Inverse tangent of something that's approaching infinity is approaching what? It's approaching pi over 2. This might be a way to get a computer to come up with a good 200 decimal place approximation for what? Pi. Try it. Try it in Maple and see what it comes. Now, Maple defaults to 15 or 10. I think 10 decimal places. And you can get it to do more decimal places by what? Digits, colon equals 15, or digits, colon equals 20, or whatever. But this would be a pretty simple, that's not a real complicated supercomputer looking problem, right? Pretty simple looking problem, and the answer to it is pi, so it'd be interesting to see what that would look like in Maple. So if we could, back to our rough sketch, we evaluated this region, and in a sense we got pi over 2. Therefore, this other region is also pi over 2. So the area of this entire region under this curve from negative infinity all the way to positive infinity is a nice clean value pi. So converges, right? This integral converges.
Symmetry.
If you don't, then you're going to have to find a value where you're going to kind of stop one region and start the other one. Right.
They're both
Right. So
convergent.
her question is, if we don't have some natural symmetry, what are we going to do? It does help to sketch it, because even if it's not symmetric like this is an even function, you might come up with one that's an odd function. Let me give an example. But that third category, so let's say it's not so I don't have the symmetric image on the other side of the y-axis, but I've got the symmetric image on the other side of the origin. We could still break this up at 0, right? And this, in essence, would be positive right? Because it's bounded between the curve and the x-axis. This region would be
Negative.
negative.
It'd give us 0.
So the net is going to be 0 if, in fact, it is the curve that looks just like this. But we do have to actually deal with that slightly differently. Because if this piece diverged and this piece diverged, we can't, even though visually we think they cancel each other out, if one of the pieces diverges, it can't really be helped by the other one, regardless if it converges or diverges. So you could split this up into pieces, and then ultimately the answer would be possibly, if this diverges, so does this, therefore the answer diverges, even though we think they balance each other out.
Okay.
But somehow find a place where you can break that up. Okay, this is probably a little out of place, but we've taken a look at 2 of these situations. Let's see if we can kind of summarize these in general. Don't want that. I don't want that either. I guess I just didn't write this up. What if our integrand is of the form 1 over x to the p? Now we've looked at 2 of these. 1 over x to the 1 and we've also looked at 1 over x squared. Those were our first 2 examples today. Well, let's see if we can kind of categorize what we should expect for an answer based on the numerical value of p. Is there kind of a cutoff where when p is smaller than that, it diverges, p is larger than that, it converges? Let's see if we can come up with this. So let's just say from a, where a is some number, I don't want to put a specific number in there, all the way to infinity. So we kind of have to handle this with cases. There's one category that we already looked at when p is equal to 1. That's kind of often a category by itself, because if it's just 1 over x to the 1, that's natural log, right? This is our first example. We decided that was natural log, and we ended up with natural log of a value that, let me just put this down here. Let's call it r, where r was approaching infinity, minus the natural log of this number, whatever the number is. This is always going to be a number. The natural log of 2, that was a number. The natural log of 8, that's a number. So that's never going to be a mystery. What happens to the natural log of r as r approaches infinity? We decided that got infinitely large. Therefore, the result was the fact that it was divergent. We did not get an answer. The limit does not exist. So when p is 1, we're kind of forced to integrate this as a natural log. If p is something else other than 1, so larger than 1, smaller than 1, can't we integrate this by adding 1 to the power, dividing by the new power, right? As long as it's not 1, we use the power rule. So I'm 1 over x to the p, I'm going to call that x to the negative p. If the little a is bothering you, just put a number in there. It doesn't matter. I just don't want to kind of zero in on any one specific number. As long as p is not 1, which we've already handled that, what's the integral of x to the negative p?
X to
over negative p plus 1 to the negative p plus 1.
Okay. X to the negative p plus 1 over, I think this is what I heard, negative p plus 1, right? Add 1 to the power, divide by the new power. And we've already ruled out there's no way we're going to divide by 0 here. If p were equal to 1, it'd be negative 1 plus 1, which we'd be dividing by 0. We've already handled that case up here, so we don't have to worry about that. So if we plug in r, let's just kind of leave it alone. Let me bring this out in front. I'll just bring out that coefficient out in front so we can look at what we want to look at here. So don't we plug in that r is approaching, and we plug in r for the x value, right? Got too many letters here. Apologize for that. Again, a is a number, so don't worry about this. This is a number. 2 to a power, 8 to a power, 11 to a power, it doesn't matter. This is what we're concerned about. If that hangs around and gets larger, we're in trouble and this diverges. Is that correct? If it somehow gets thrown to the denominator and gets larger, that's a good thing, because if it gets thrown to the denominator and gets larger, what happens to the value of that fraction?
It goes to 0.
It goes to 0 and in fact disappears. What value for p would send this r thing that's getting larger and larger and larger down to the denominator?
Greater than 1.
If p is greater than 1. Is that right?
Yeah.
If p is greater than 1, just pick a value. Let's start with 2. If p were 2, this would be r, some number that's getting larger and larger, to the what? Negative 2 plus 1? What's negative 2 plus 1? Negative 1. Where does that send it? To the denominator, and it can get as large as it wants to in the denominator. What happens to that term? It goes to 0. So if p is larger than 1, well, I looked at 2. I don't know. How about 1.2? Does that still send the number that's getting larger and larger and larger down to the denominator? Well, plug it in. Negative 1.2 plus 1. What's the result?
0.2.
Negative 0.2. Where is it if it has a negative exponent? It's in the denominator. So as long as p is larger than 1, what's this thing going to do?
Converge.
It's going to converge. And if p is 1 or less, it's going to diverge. So we've already got p equals 1, it's divergent. If p is greater than 1, it's convergent. And you could try a number that's smaller than 1. Just try 0. If p is 0, what do you get? You get 1, which is r to the 1. Where does it stay? It stays in the numerator. If it gets larger in the numerator, it's divergent. If it gets larger in the denominator, it disappears and causes the integral to converge. So for this particular integral, if p is less than or equal to 1, what's the decision? Diverge? And if p is greater than 1, it's going to converge. We will revisit this problem in a slightly different manner later in this course when we get to Chapter 8. And we'll talk about series of progressions of numbers that are called a p-series for this very same reason, 1 over x to the p. And we'll see similar results. So the fact that we've done this problem kind of generically, let's suppose that we had this example right here. We can't completely do this problem, but we can make the decision, is it convergent or divergent, just based on what we have right here. It's convergent, right? There's p, 1 over x to the p. So p is equal to 3/2. We've got the same format set up, 7 to infinity. So as long as p is greater than 1, that's going to eventually send the bad value, the number that keeps getting larger and larger, down to the denominator. When that happens, that's a good thing. It disappears. Therefore, the integral converges. Now, what we can't answer with this is, okay, we know it converges. What number does it converge to? We'd have to actually do the problem to do that. But we can determine that it's convergent. Okay. Finish with this today, but let's say that we have some curve here. And I'm not going to specify what f of x is, but we know we can start at something. And we know that if we let it run all the way out to infinity, that this is convergent. Okay? We have another one that starts at the same value, and we know for a fact that it's either equal to or less than the one that we began the problem with. What do we also know about this problem? It also converges. I heard that from a couple people. Does that make sense? So if the curve that I wrote in black is a convergent integral from a to infinity, anything less than or equal to that is also convergent. So certainly, if we're going to be able to find the area under the black curve from a to infinity, we will also be able to find the area under the red curve from a to infinity. So this is going to seem overly simplified, and you'll think less of me for saying this, but if someone walks into the room and they're a diminutive human being, they're small, okay? So I don't know what that conjures up in your mind. Let's say this person walks in and they're, I don't know, 4'8". It's a little person. It's a third grader, okay? They walk in the room and they're 4'8". And everyone in the room would say, oh, well, that's a little person. Okay? They're small. Okay? Someone else walks in right after that little third grader, and they're even smaller. Wouldn't you say that person's small too? Right? So if that first person was small, and the next person's even smaller, you're not going to say, oh, that's a huge person. They're humongous. No, you're going to say, they're smaller than the one that came in before. Clearly, they're small, right? Smaller than small is what? Small. Okay? That's what this is. If this one converges and we've got one underneath of it, see, I thought you'd think less of me. This one's even smaller than this one. It has to converge. Okay, now let's get the analogy on the other side. I taught Todd Fuller here when he was a basketball player. He's also a math major. Lives in Charlotte now. Really, really neat person. He's 7 foot tall. So Todd Fuller walks in the room, okay? And we all think, oh, man, he's tall, okay? And then we have someone else, Manute Bol, walk in the room who's 7'9", okay? Do you think, oh, Manute Bol, he's just a tiny little person? No. What do you think about him because he's taller than Todd Fuller? You say, man, he's really tall. He's tall. So what's the analogous situation to this problem? And we'll start class with it tomorrow. If we've got an integral that is divergent, and we've got another one that's even higher up on the axis system than this one, what does it also do? It also diverges. Because if it's considered to be large, what would you call the one that's larger than it? It's also large. Okay? Humongous. Okay? We'll continue this inane thought tomorrow.